Thank you very much for the kind introduction, and I am deeply honored to be here today to give a keynote speech. So, before I start, I would like you all to ask yourselves, what hooked you into robotics? For me, it was this blue robot called Rosie from the cartoon The Jetsons that would do all the household tasks. It would deliver the food and drinks to George Jetson and the rest of the family. Just like this robot in this picture delivers this pair to me. So the question that we will try to answer today is how can we enable such mobile manipulator robots to work in unstructured, human-populated real-world environments? And I will show you 5 points in which we can deploy structure in order to scale robotic behaviors to allow them to enter the unstructured world. And well, growing up, I realized that there are more pressing conditions beyond just having a household robot. So the journalists have been reporting the immense shortage of healthcare workers in various countries of the developed world, revealing a shocking extent of staffing crisis that threatens the effective health coverage. But this goes beyond hospitals. Let's look at some data. The age population, people aged 60 years old or over, they reached 1 billion and they keep increasing. And on the other hand, COVID-19, digitalization, the offer for working from home had made many people to opt for higher paying jobs than the one of caregivers. And this means that seniors are stuck at home alone. This means only one thing. We need robotic assistance. And in order to fulfill this vision of robotic assistance, we need to unlock the path to embodied intelligence through mobile manipulation systems. And why do we care about mobile manipulation? Where they combine mobility and manipulability such that they can move around and manipulate objects in the world. They are equipped with multiple sensors such that they can perceive the world around them. And they have an increased workspace as the whole world is their workspace. And as mobile manipulation systems are actually structured robotic systems, let us now unveil what do I mean by structured robot learning. So I hope you all know that robot learning is the field that uses machine learning in robotics to allow robots to acquire skills through imitation and interaction with the environment. Now, to give you the gist about the research in my group, IROS, we take into account the structure of the problem to enable faster, safer, and scalable learning of robot behaviors. And what can we achieve with structured robot learning? 3 key properties that, in my opinion, are necessary for the robots to acquire behaviors like the ones of Rosie the robot. First, coordinated and generalized manipulation skills. Next, fluid and safe human-robot interaction. And third, scalable long horizon behaviors. And now I will point you to 5 key areas in which structure couples with robot learning to give us a flavor of our desiderata of assistive behaviors. But before we start, let's take a look at this handover scene. The robot needs to understand the intention of the human, and it needs to effectively coordinate and position itself into the environment and be able to understand grasping actions up to the delivery of the object, and most importantly, it should act safely. And this is where structure comes into the game. So first, we will see how we can structure models for effective human-robot interaction. Then we will see how we can exploit the scene structure to learn long horizon behaviors for manipulation. Next, we will see how we can exploit the structure of the robot itself as a prior for learning mobile manipulation. We will arrive to the point of seeing how we can learn data-driven objectives that can also be structured, arriving finally to the crucial point of safety, where we will see how we can learn and structure constraints. Well, we will see all these points in some different but representative test beds, but they all contribute to my idea of scaling robotic behaviors for assistance. So my first experience with robotic assistants was during my PhD when I was studying models of human behavior. So the objective was to actually develop algorithms to control this mobility robotic assistant to help elderly people with various mobility issues like Parkinson's and so on, to provide them support and act proactively. And we realized that effectively patients with different pathologies have different walking patterns that are way different to the one of the normal gait cycle. And for that, I developed a structured walking model with which we were able, only from laser data, to track the human and also do gait analysis online such that we can also assess the rehabilitation process. But then we question ourselves, how can we use this information to actually control the mobility assistant? To formalize this problem, we viewed it as a human-robot couple navigation problem in which the robot is effectively always in front of the human and it has to maintain a specific distance and orientation that has to be also relative to the way its human walks. And from the different approaches that we could have used, we hypothesized that using a human-centric model-based reinforcement learning approach can allow us to learn the interaction dynamics of this challenging human-robot interaction scenario. And we can also deploy a human motion intention model that allows us to predict the walking intention of the human in the future, and then deploy model predictive control in order to decide over the optimal action of the robot. And our evaluation has shown that yes, indeed, learning the interaction dynamics matters, as the model-based reinforcement learning approach yield much better results than other classical approaches. So we took an idea of what it means to structure models for human-robot interaction, and now we will see how we can exploit the scene structure to learn long horizon behaviors. And as a testbed, I will use the problem of assembly discovery. And what do I mean by that? So imagine that you have a designer or an architect that gives you an abstract shape and some building blocks, and you have to exploit them in order to fulfill this abstract shape. You don't have any further instructions. This is a combinatorial optimization problem because you need to find the effective placing sequence of the building blocks. This looks like this. So you have some building blocks here with yellow are abstract designs in different planes, and we need to find the combinations. So we thought that if we exploit the scene graph in this problem, we can actually apply a graph neural network in reinforcement learning in order to train an agent that can discover relational sequential task sequencing. And actually, when you use this agent during inference, deploying also search in an AlphaGo style, we have seen much better generalization in terms of new scenes with more objects in the scene, different kinds of structures, or like more planes that you have to fulfill. But obviously this task revealed that this is a hard exploration problem because of the combinatorics. And today, Niklas Funk presented here an hierarchical approach that decomposes this problem. So in particular, we proposed a hierarchical method where on the high level, we define a reduced version of the problem where we solve mixed integer linear programs to find the block type and the end poses in the structure. On the medium level, we deploy the graph-based reinforcement learning agent that now only explores on the feasible solutions provided by the high-level MILP. And on the low level, we have a grasp and motion planning approach, a classical method for transforming the desired assembly commands of the medium level into robot trajectories. But let's get some more insights about the high-level MILP. Imagine that your robot has to play 3D Tetris, right? So the blocks might look a bit like this. This yellow design is this abstract design that we need to fulfill. And if we see it in 2D, it would look a bit like this. And in 2D Tetris, usually you have like a rectangle area that you have to fulfill. But in our case, we only need to fulfill this pink area that it is included inside our design. Now, in this part of the problem, we do not care about structural stability, we do not care about robotic feasibility, and we do not care about the task sequencing. It's a reduced problem. The MILP here only resolves on which block type we should place where. And now comes the graph-based reinforcement learning agent into the game. So we create a scene graph that contains both the placed and unplaced blocks and also the voxels that have been fulfilled or should not be fulfilled. And through several rounds of methods passing and while exploring on the feasible solutions provided by the high level, we are able to learn the task sequencing. And importantly, at this stage, we take care of the structural stability as this is part of our reward function. We care about robotic feasibility as this is also in our rewards. And finally, we learn the task sequencing, deploying this Grassman motion planning low-level trajectory planner. And we have shown that, yeah, sequence matters, because if we just deploy the heuristic, we end up with several collisions, while our approach, while using also search in real time, yields much better results. And also, it allows us, by deploying a digital twin, to transfer directly into the real world without needing any further retraining. And what is also important to note here is that this agent also has an additional action that allows it to decide when it should stop the building process because it fulfilled the design. So it is pretty common that you have more building blocks than you need. So yeah, the agent generalizes pretty well in new scenes with unseen block types and so on. So now we will see how we can exploit the structure of the robot itself as a way of learning effective mobile manipulation. So mobile manipulation is very difficult because you have to coordinate different embodiments. And Snehal Johri, that now won also the Best Paper Award in mobile manipulation, has shown yesterday that we have to use actually a hybrid action space. And what do we mean by that? In our case, the hybrid action space is a continuous action space on the base placement, so position and orientation, and a discrete decision variable on whether or not we should activate the arm in order to execute a manipulation action. Now, in order to deploy this in our favorite deep reinforcement learning algorithm, we need to define a hybrid policy. And in this policy, we have a continuous part of the policy and a discrete part of the policy that is conditioned on the continuous part. And in order to train this, we, with automatic differentiation, we have to exploit also a Gumbel softmax reparametrization trick. Yet, in order to understand when we should activate the arm in order to manipulate something, we need to have an intuitive understanding of the robot's reach. So for that, we rely on classical robotics. And we design the operational workspace of the robot that intuitively tells you what is the frequency with which you can reach different 6D targets in the workspace of the robot. And if we consider the floating base scenario and we do the inverse mapping of this operational workspace, we can find the potential robot poses that can lead to reaching success of arbitrary 60 poses. And here, how does it look like? And with blue, we have the poses with probability of higher success, let's say, or frequency to be more precise, for this 60 target. And then we thought, what if we actually train an agent to use this information in order to acquire a smooth Q reachability map? And this is how this looks like. As you can see, it's smoother, it interpolates over the different poses, and it considers all different orientations for the base poses, although here it's reduced version for visualization purposes. And this refers only to this pose. Yet again, this is an information that it is in the locality of the robot. And in mobile manipulation, we need to resolve more, let's say, long horizon behaviors where the robot needs to move around in the world, as we said before. Therefore, we introduced boosted hybrid reinforcement learning. And this algorithm allows us to model the Q function as a sum of residuals, such that every time that we transfer to a new task, we only need to learn the residual of the Q function that is missing, effectively keeping the structure of the knowledge about the previous task untouched. And additionally, we saw that if we deploy a forward Kullback-Leibler regularization, we can give intrinsic bonuses to the agent for remembering some good actions. And this effectively handles changing observation spaces across tasks. And we can arrive from just simple reaching of 6D targets in different radiuses to navigating across obstacles and reaching, fetching objects among obstacles, and also finding like clearance for grasping objects when there is the table is populated with other unwanted objects. And we can transfer, again, this behavior directly into the real world without, again, needing any further retraining on the real world. And we can see that our robot is able to place itself effectively. And what is important to understand here is that our approach is a higher level approach. It gives us out some sub-goals that the agent needs to reach with our favorite motion planning or reactive control, whatever we want for navigation. And we can effectively also use the same smooth Q-reachability maps for resolving rearrangement tasks where the robot has to take the objects from the one table and transfer them to the next table and so on, as basically it has an intuitive now understanding of the reach and how it should place effectively itself. And it only takes a few steps to realize these tasks. But when we talk about manipulation, we don't only care about pick and place. There are tasks like pouring water in a glass that you cannot effectively design the objective. And in these cases, you have to learn them from data. Now, yesterday, Anti-Lair introduced a method for learning implicit priors, or if you want, cost functions for motion optimization. So given a set of some trajectories, we propose to use energy-based models to learn our implicit priors. And why do we care about energy-based models? Where they can capture the multimodalities in the data. They are composable such that they can be combined with other objectives that can be learned, or they can be hand-designed. And they can be represented in any space. As for example, we can learn them directly in the task space and effectively plan with forward kinematics and evaluate the trajectories. But let's get some more insight about how we can use energy-based models in trajectory optimization. So we have to take a planning as inference perspective. And in this case, the trajectory optimization can be formulated as a maximum a posteriori problem, given that we have also some initial distribution. Now we can factor this prior distribution, especially if they belong to the exponential family as our energy-based models. And with that, we get structured planning objectives on which we can also add contextual a priori priors, for example, initial explicit distributions about like initial trajectories and evaluate them on the learned ones. So this is what we get. From some initial expert demonstrations, we get the energy landscape, and then with additional objectives about smoothness, we get a smooth trajectory over planning for different sub-goals. And effectively, we can also learn pouring tasks in which we learn the initial landscape by demonstration. And then we show how we can combine this cost function with additional cost functions on smoothness and also of obstacle avoidance. And no matter how we change the scene, the agent is able to actually fulfill always the pouring task without losses. And moreover, we have shown recently that we can deploy diffusion models. That is actually quite a trend right now in image generation, in order to learn manifolds of objects in SE3 and have the graph distribution in SE3 by diffusion. And by having these graph distributions by diffusion and having the direct access to the gradient, we can employ stochastic gradient Langevin dynamics and plan by diffusion, and in a single optimization process to be able to resolve the effective grasp and base and placement of a mag, like in this case, in the Buchself scenario, given additional objectives for collision avoidance. And finally, we arrive to the final point of how we can safely plan interactions or manipulations. And we will see how we can learn constraints. Now, yesterday, we have Putelu introduced the regularized deep sign distance fields. Now, deep sign distance fields are commonly used, as you know, for defining obstacle avoidance objectives. However, they are a bit challenging to actually design. Now, with our approach, we are able to effectively learn at any scale the sign distance fields of articulated objects like robots, because we deploy also a regularization term with learnable parameters that allows us to effectively learn the zero level set of our sign distance field, which means that we can reconstruct with great detail human manifolds and also have smooth distance fields at any level. And here you can see an example of how we can effectively, smoothly change the level set while interacting with the robot, and while the robot approaches the human, this collapses, let's say, to the human manifold, representing some sort of safety layer over the human. But to learn the human-robot interactions, we need to guarantee some sort of safe exploration in our reinforcement learning agents. And for that, while other approaches would reject bad actions or add a safety layer, we choose to act on the tangent space of the constrained manifold. So we effectively construct the constrained manifold. And we have shown that we can use these with generalized nonlinear control-affine systems. And thanks to the Jacobian of our system and also of the constraints, we are able to have a direct mapping from the actual action space to the actions in the tangent space, such that we can guarantee that we never violate the constrained manifold. And this allows us to learn challenging tasks like reactive navigation with differential drive constraints, where we have also a random agent here, which we have to avoid, and also the collisions with the environment. We can deploy our learn distance field directly because we have access to the gradients, and learn reactive manipulation in constrained environments like the bookshelf, and also transfer it into the real world without losses from sim to real gaps, because our constraints are always active. And finally, we are able to learn human-robot interactions. This is a scenario of, let's say, shared workspace, where the robot has to deliver a cup to the human, just like when Rosie was delivering a glass of water to George Jetson while he was reading the newspaper, while in these cases, the human just looks at the phone. And you can see here that no matter how the behavior of the human changes, the robot is always able to avoid collisions with the human that moves, let's say, dynamically into the scene, and also with the environment, so the table, the robot itself, and without turning over the cup that it has to deliver. So I have walked you through 5 points in which we have seen how structure can be used in robot learning for scaling robot behaviors. And while we have seen these points in different test beds, they all can come together in order to learn and scale mobile manipulation to effectively achieve this vision of intelligent robotic assistants. And if I can give you a takeaway message, I believe that we need to remember that we stand on the shoulders of giants. We need to effectively combine our knowledge of classical robotics and augment them with machine learning methods, such that we can scale them up and create hybrid methods. We need to use the structure of the problem. This is the way to scale robot behaviors. We need to structure models of human behaviors and also consider the actual manifolds and not just skeleton representations of humans, as this is the way to acquire smooth and safe human-robot interaction. And finally, I think that we should put our focus on learning mobile manipulation skills, as this is the way to embodied intelligence in order to acquire the vision of intelligent robotic assistants. Before I finish, I would like to tell you that I am hiring PhD students for spring summer 2023. So if you share the same vision with me, please reach out. And with that, I would like to thank you, and I will be glad to hear your questions.
So we have 5 minutes for questions. Just go on up to the microphone. Yep.
Thank you for the great keynote talk, Georgia. I was wondering, you already in the end tried to combine everything that you presented today in one structure. I wanted to know how you envision combining everything from leveraging structure, especially on the focus of human-robot interaction for some kind of long-term task, because so far, as I understood, you considered it as a moment right now where the human is interacting with the robot, but how you envision leveraging the structure for effective human-robot interaction.
Thank you very much for this question. What we are working on is actually creating these intention models. There is a work that we presented last year in ICRA where we have shown how we can have structured predictive models of whole body human motion prediction with graph neural networks. And we can effectively consider deploying these in order to predict into the future what will be the behavior. But I am also considering also multimodality in which the human could also express, for example, what it wants or like do gestures of what it wants. So this is how I envision it. Here, most of the part that I've shown didn't have the aspect of the perception. So this is the part that we are also integrating. But yeah, thank you very much for the question.
Really cool. Looking forward to the next works.
Thank you.
Hi, thanks for the great talk, Georgia. I was wondering with the videos with the human interacting with the robot, the human was moving quite slowly. And have you considered if humans might move more quickly or unexpectedly?
Yeah, definitely. So in this real world transfer that we did, we wanted to, since we didn't deploy any predictive model of the human, and given the frequency in which we could actually control the respective robot, we instructed the human subject to act, let's say, a bit slowly. But in the end of the day, we saw that progressively the human somehow gained some kind of confidence. Of course, I don't have data of human studies on this. It's something that we would like to do into the future. But definitely you need to consider like higher frequencies. And for that, we need to have also the hardware that allows us to act on these frequencies. But in terms of control frequency from the network, we don't have issues. So it's on the other end that we need to resolve.
Right. Thank you. Very cool work. Thanks.
Thank you.
We have a
Hi,
question.
Georgia, great presentation.
Yes.
So could you give more comments on the relationship between learning in mobile manipulation and the embodied intelligence? The last conclusion.
Yeah. So, I mean, we can see that mobile manipulation system, and this mobile manipulation system, first of all, doesn't have to be always a system that has wheels. It can be anything that can move in the world around it and manipulate, can instantiate, in my opinion, an embodied AI system because it's equipped with all the sensors that you need in order to perceive the world. It has the capacity to interact and change the environment. And since you can change the environment, this is actually the definition of acquiring embodied intelligence. And this is what we as humans mastered. So yeah, I don't believe that we will arrive to the level of human behavior, but I think that we can scale up intelligent assistants such that they can interact at least to a level, repetitive tasks and so on with humans in day-to-day environments.
We have another
Thanks.
question.
Yes.
One more question in the back.
Yeah, hi. Thanks so much for the inspiring keynote. So a lot of your work is about exploiting sort of algorithmic priors, right? Or structural priors in a way. To what extent do you think this kind of exploration will be necessary as hardware becomes more powerful, as end-to-end learning methods maybe become more and more powerful? So where do you think the maybe long-term requirement for this kind of exploitation is?
I think that data are very important because part of my work actually exploits experience. So we should not like consider that the two, the two ends have to be decoupled. Actually, we need to find the sweet spot. And effectively, I think that since robots are structured systems, or at least the robots that we are working with are structured systems, I think that we should deploy this information, even if the hardware becomes more powerful. Therefore, I think that this is the way to scale it up and not only consider that data will give you the information that you need. Like effectively, I think that we as humans during the so many 1,000 years of evolution have some pre-encoded prior. So why shouldn't we exploit them for robots? Clearly robots, it's a different system than computer vision, for example.
Thank you very much.
Thank you.